So this is me during my many years at Similarweb. Similarweb, for anyone who hasn't heard, we track, monitor, and analyze internet traffic around the world and provide our clients with a variety of solutions, but the best known one is for doing digital market research. Unlike classic data engineering, we first collect data from all over the internet and then make it accessible to clients. Clients can ask questions like, what is the size of a certain market? They can get recommendations on search terms, track campaigns against competitors, and see who captures more market share. And we have a sales intelligence solution, kind of like Zoom Info, but more digital, more focused on advertising companies looking for leads. All right, this slide, this is where it starts to get interesting. This is a very typical schema in my group for making data accessible from our data lake to production. Our back-end developers handle back-end work for both the UI and API, but also manage lots of pipelines that aim to take raw data, transform and load it to our production databases for end-user consumption. Again, at Similarweb, we make the entire internet accessible to all customers. Okay. How do key-value systems compare to SQL databases or execution engines, and which do we use when? I'm going to focus on DynamoDB and Firebolt as specific examples. In terms of performance, there's no real competition between key-value and query engines, for the simple reason that in a key-value store, we directly access the relevant key. Think of it as a very simple hash map. There aren't really any challenges, whereas a query engine runs more complex queries requiring more CPU and RAM. The memory usually holds much larger volumes of data, resulting in much longer processing times. In key-value, there's no issue accessing the key, deleting, or updating. Very dangerous for anyone who's kept terabytes or more, certainly in relational databases and especially in any big database solution. They always say it's supported. I wouldn't recommend it. When we encounter complex queries, this is where SQL is significantly favored. Anyone who's experimented with the more advanced MongoDB solutions and the like, and tried to run really complex queries, especially when it comes to joins, or trying to create all sorts of views, things become very complicated. And this is where query engines enter the picture, which allow us to get much more complex and interesting insights from the data. Costs, we'll talk about that later. So first, regarding what I call simple analytics in DynamoDB. What is Dynamo? It's an AWS managed product. First of all, it really is fully managed. There is no need to deal with optimizing the database or the DevOps behind it. Truly serverless. You don't even need to configure anything related to the engine. Global table is a great concept for anyone who cares about long-term stability, or if you're working with active-active, an out-of-the-box feature. And reliability. It's one of the most stable services I've ever encountered. A classic example of when we'll use key value is time series. A very simple concept. Who can guess which website exploded in December of 2022? ChatGPT. And this is a classic graph Similarweb uses to show time series on lots of metrics. Of course, I took the most simple examples. So the idea is that in this case, I take a domain, a website, and a date. For instance, day, month doesn't matter. So this is how we divide the graph over time. Of course, we analyze longer time frames and compare competitors. We retrieve in batches, which is another feature supported by Dynamo. And here comes the catch. All manipulation happens in the code. We don't run scans in Dynamo. it's very expensive and inefficient. So if we're talking about filtering, aggregation, even the simplest, it happens in the code. At these volumes, it works very, very fast. We can reach very high speeds. Dynamo handles it without issue. So we will always choose this option when we're talking about very simple data sets, where the user more or less gets the raw data that exists in the database, as is. Read-write capacity. This is how pricing is calculated in Dynamo. Not for the faint-hearted. A bit confusing, but bear with me, okay? There are two payment concepts in Dynamo. One is on demand, simpler pricing. $1.25 per 1 million writes, 25 cents per million reads, and I have no other restrictions. This is a very high price at scale, but it really lets me enjoy peaks without feeling them. Now, if I want to optimize, Dynamo created the term provisioned, where the price is very low, but I'm limited on writes. So at Similarweb, where we write in batches, either daily or monthly in most cases, we increase the write limit before writing and reduce it after writing. But there's a limit on the number of changes per day. So if we have a problem with the data, it gets complicated and we switch to on-demand and it's a mess. However you look at it, writing 7 million records a day comes out super expensive. And we really suffered with Dynamo tables that kept growing. We nagged Amazon for at least 2 years to give us the option to do a batch write or to upload a file to Dynamo. What we would do is run a Spark job, writing one by one. It might have taken a reasonable amount of time, but it would cost a ton. So the concept of load from S3, it lets us take JSON or CSV, push it in a managed way. It's not some function we run, it's just an upload that's a Dynamo function, and as you can see, the price is simple. And here's a real example of what happened with one of the tables, how the price dropped because we didn't have to maintain a Spark cluster for writing or pay per read to fix issues. On demand, not on demand. I warned you it's not for the faint-hearted. But there's always a but, right? Right now it's only supported in new tables. An update is coming. Like the Postal Service, it'll probably take maximum 3 years. So we live with it in relative peace. That is, when we create a new month of data, we write it to a new table, so the API calls are per table. The infrastructure works, it works well, but it's frustrating. All right, to the next example, where things start to get complicated, a real-life example. Take Amazon versus Walmart. Real players in the US competing for numerous search terms. Here you see a table with 10 million search terms for a specific month in the US. And here I want many more statistics, searches, manipulations, and filters, which to do them in memory at a certain point isn't feasible. It doesn't move. We did many POCs for this use case. We started working with Firebolt about 4 years ago. What's Firebolt in a nutshell? First, it's a very, very fast columnar database. At the core is an extremely powerful engine that allows us to efficiently scan terabytes of data and return queries in extremely short time frames. The concept of compute storage separation, we can write a table or database one time and have many clusters access it for different needs, for reading, writing, with total separation between them. One database could fail while another remains unaffected. Okay, built-in warm-up mechanism. This is a slightly complex concept at first, but it's important to understand. The moment I query, scanning S3 will always be slow because there's a download time. What Firebolt gives us is out of the box, instead of creating all sorts of caching layers. In the first query, I felt the download time from S3. The whole downloaded chunk stays on my SSD, and from that point on, the latency is practically non-existent. I only experience the query time, which is very fast. Sparse indexing, also an important concept, especially for analytics. It allows for very fast scanning using indexes, and of course also a managed service. We choose the cluster size, but don't deal with any maintenance beyond that. The concept is similar. Here we typically load ORC or Parquet files. There are many other formats, but we won't get into them right now. The idea behind Firebolt engines is that as soon as I ingest my data into Firebolt's S3, I can spin up engines for whatever purpose I want. For example, in our case, one engine costs $5 an hour, active 24/7 to serve queries to the UI. A second engine, more powerful, serves queries to the REST API because here I need slightly faster performance and higher concurrency. And once a day, I launch a huge engine that writes for an hour. Everything runs simultaneously without bothering each other. This concept doesn't exist in the older RDS. Today, gradually everyone is adopting it, but in Firebolt it comes out of the box. Here's an example of a keyword query. You might not see it, but there are dozens of lines. Trust me, it's complex. And we're talking about a table that's 72 terabytes compressed and over 300 uncompressed. Lots of keywords. In the end, we were able to reach a response time of 70 milliseconds and scan only 80 megabytes out of all this data for the keyword iPhone. Data ranges. It's a concept that may not be trivial at first, but once you get used to it, it makes a lot of sense, especially when you're not really exposing all your data to customers and you want to have a situation where the query will take a few more seconds for the first client and then the data will be ready for true sub-second querying. So let's say my data comprises many domains, each with numerous URLs, content pages. So let's say I have Amazon and Walmart. What happens is I wanted to find all the pages containing the term shoes within all of Amazon URLs, and this is how the index is built. The second I took this, I already loaded all the data just from Amazon. So Walmart stays in S3. Amazon enters my SSD. But right now I only asked about shoes. When I ask about laptops on Amazon, it's already in the engine's SSD. There's no download time. All I have is the net query time without any caching on top. There are many Presto caching solutions. Here it's out of the box. Okay, indexing. As a Firebolt design partner, we've seen many iterations of the sparse indexing mechanism. I will present a very simple concept, but it's something that needs emphasis, especially with large data sets. Less than a tera usually, no problem. When we get to tables of 200-300 terabytes, things start to get complicated. And then it's very important to understand what your typical query looks like. In this simple example, I have a table with products, and I want to analyze by brand name. So not surprisingly, the brand will serve as the index. What Firebolt also allows is the concept of an aggregating index. That actually saves me ETL. I can say, okay, I want maximum performance even when querying a category. So I'll create another aggregating index on the category, and every time I input data, a view will be created, and it takes up some space, but this happens in the background, and it'll allow me to reach maximum speed for additional columns. Apart from that, there are all sorts of other tricks, but whoever is interested can contact me offline. Thanks very much.